on hydraulic modeling. Here we go. Okay, there we are. Okay, and there you go. They will be speaking on hydrology for today. Thank you. Yeah, yeah. Hey, okay, take it away.
All right, thank you everyone for having us once again. My name is Julian Hernandez, and this is my coworker Ken Chow. And kind of piggybacking off what you just heard, we're going to be kind of showcasing what we're using this LiDAR data, how we're using it, and it's going to be in regards to modeling the urban hydrology within LA County. Okay, so just to give a brief background, if you look to the right side of the screen there, you see the area of focus, and that's the LA County watersheds. And to the left, there's an illustration showing a watershed area, which is a body of land that collects water by way of rivers, streams, and then drains into a specific point, into a specific water body, such as a lake or an ocean. Now, this illustration, this is a natural landscape. But when we're considering the landscape for LA County, it's much more complicated than that. So here we see an example of what we can expect to see within the different communities of LA County. It's very busy. There's high density residential areas, commercial areas, single family homes. But ultimately, we still want to be able to identify where our water that's falling onto the ground, where it's actually going, the route it takes, and where it's being emptying out, whether it's a reservoir, an open channel, or the ocean. Now here's the objectives and goals of our project. In order to complete this task, we use the derived continuous flow tool within ArcGIS's hydrology toolset, which enabled the modeling of water flow across the county on the surface of the ground. And what we'll be discussing is that surface flow, the storm drain network, to follow the underground route that the water takes. The right table that you see there kind of shows a few statistics regarding our SDN network. We're also going to speak on creating a connection between these two data sets, the surface and the underground network, identifying errors that we ran into, and at the very end, merging all of the LA County major watersheds into one data set. Now this slide shows just an initial basic workflow for our project. For the surface elevation, we used a high resolution digital elevation model, or DEM for short, which was obtained through the LARIAC program. Now, with the Esri hydrology toolset, the derived continuous flow generates a raster of accumulation flow on the surface. Now, the flow direction and flow accumulation derived, it's on a cell-by-cell basis. It traverses the input surface raster by following the direction of the minimum upslope neighbor, as you see at the illustration there at the bottom. Now, this tool is not sensitive to errors within the surface, so there's no depression or sinks that terminate the flow. Filling the sinks or depressions was not necessary for us. Now, the catchment areas were then generated using a flow direction raster that is produced from generating these streamlines. And we'll demonstrate the workflow that we took with further graphics in the following slides. And for that, going into more detail regarding the model builder that we used to create these streamlines, I'll pass it over to my coworker, Ken.
Hi, good afternoon, everybody. Today I'm going to explain how our model is work, what data source is needed. As you see in this slide, we are using the DCF, Drive Continuum Method from the Esri Hydrology toolset to generate the surface flow and the catchment area. In this project, we quite often using very large data set and then a lot of repetitive process, complex analysis, sometimes that not easy to use and user friendly. So our unit is to design one of the model that is easy to use and then two major input needed. So first input is depression data or catch basin data set. The other one is DEM, digital elevation modern surface raster. If you input in these two data set, run it with our model, they will be generate surface flow and then catchment area. So our model have two parts. First portion is generate the surface flow. Second part is generate the catchment area. Next, this slide is showing that we created the surface flow along the street. It is continuous flowing along the street without stopping. Second part of the model is we are creating catchment area. Using our surface flow and then depression data, that will be generate the catchment area. This is second workflow. We have to create it pseudo lines. After that, we generate it integrated with the storm drain net, and then we create the trace network. This is another model we created for the creating the pseudo line. Before we're talking about on the slide in the right side of we have a photo of catch basin location on the street. The catch basin is really part of our project. The catch basin is where the surface flow water going into the underground. So that's just explaining that's the catch basin location. And then explain about the monomer. We have to create the pseudo line because not all the catch basin is on the surface flow stream line. So we have to create pseudo line and then connection with the surface flow. Then the surface flow is one into the catch basin. So that we create complete surface flow one into the catch basin. That is some of the example of creating pseudo line to the catch basin or from the catch basins. This is a result of creating the surface flow. And then next, creating the catchment area. Then the other one on the right side is the total surface flow it one into the catch basins. So after we creating the total surface flow one into the catch basin, next step is to integrate it underground layer from the storm drain net. That is showing our hydrological total data set is work. As you see on the slide, the purple green layer is above the ground surface flow that went into the catch basin. After the water went into the catch basin, the water is carried on the underground layer from the storm drain net. As you see, the light yellow layer is the lateral line, then water is carried on the underground to gravity main, and all the way to open channel. After we creating this hydrological data set, we will use that data set to create the trace network, and then my colleague Julian will be explaining how the trace network is worked and then what error we found. Julian.
So once again, here's an example of the trace network, the components that went into building the trace network on the left, and as well as some of the errors that we had run into once it was all put together. Now, when running the new trace network, we needed to make sure that when we encountered these errors, they had to be fixed locally, but it wouldn't correct the problem completely. So we had to work along with ITD and the SDN unit in order to implement certain rules that would mitigate the errors moving forward. And if you notice the image there, there's blue arrows showing the direction that the water flow was going once it hit the gravity main. But if you notice down to the bottom left, there's a red question mark, and that's because that's missing infrastructure that we had not available to us, at least at the time. So when trying to do a trace, the flow would stop at this location. So this is something that we would run into, and we have to try to reach out to these cities or different departments that may have this information in order to add into our trace network, which would then allow the flow to continue to the very end. Now, some of these components are available for you to download through our LA County Data Hub. You just have to search for Storm Drain Network, and you may be able to download this for your personal use as well. Now, here's an example of the results that we had once we combined them all and the errors were fixed. As you can see in the very left-hand side, we placed a point, and these points could be placed anywhere throughout the trace network itself. And we did a trace upward. If we look into the center, we see the extent that it's collecting. And then the very right is the full extent of the Dominguez Channel watershed. We see that singular point from the very left collected all the water on the very right-hand side. Now here's an example of a downstream trace. I know it's not as dramatic as the previous slide, but this is very helpful for us, especially when trying to find the path of that a certain stream or perhaps a pollutant may get into our storm drain network. We can see exactly where it's going to end up by placing a point at the very top elevation and then doing a downstream trace. Now, my coworker Ken is now going to speak on merging all of the watersheds within LA County.
Hi, sir. As you see on the slide, after we finish an individual hydrological data sets for each watershed, then we combine together. The blue color is the Santa Cruz River watershed. The red one is LA River watershed. After we get the data set, we combine, much together, and then we combine with the San Gabriel River watershed. Next one, we combine with the Santa Monica watershed, and then Dominican Channel. So as you see on the right side, we have a total complete whole LA County as a whole unit. Next, what we are going to do with our data set, we will be publish the trace network for mapping applications. That application can be used by our department and also for the public. Second, like I said, Michael, we will be investigate any pocket area we left out without the infrastructure data from the city. So recently we connect with the city and then to get the information to filter any pocket area left out. And then next step is what we are going to do with our data set or future analysis. We will be generate report for any area of the interest by the city or by watershed or by supervisor district. We can break down into land cover classes. We can break down into user type, land use type. Another one is we can create an integrated water flow model with the volume. Another one is like, you guys remember 3 years ago in the Dominican Channel, something happened is really like a bad smell, something coming out, a lot of residents complaining. So it is happening, similar situation happening. We can use our data source, hydrological data sets and trace network. We can trace down the pollution location, pollution source, and then we can easily to identify what is the resident will be affected. So we can use our model. Next, we can do the stormwater infrastructure model. So, and thank you everybody again. And then if you have more questions and then information, please email to us. Our email address is mapping@www.lacounty.gov. Thank you.
Yes.
I just wanted to go back to the Dominguez Channel and just show point on the map. I didn't get the detail of what you were showing.
This one here?
Yes.
No, that was
One more.
Oh, sorry.
yeah.
Yes.
Can you just kind of walk through and say what's the What are you showing here?
So just as I had pointed out in the previous, the previous map, this one, there was a starting location is that green dot in the channel itself. So that this is an upward trace, so it's showing the collection of water at a higher elevation to that point.
Got it.
So for the next one, what we did is placed a point at the very top.
And is that the upstream?
That this is a downstream.
But that, it goes up.
It goes down, yeah. It's going down into the ocean. This is the Malibu area.
Okay.
And yeah, so the reason that it's not as drastic as this is because it's just following the lowest elevation point all the way down.
That's cool.
Mm-hmm.
Thank you.
Yeah, of course. Yes.
So do you use this to estimate flooding with the high volume of water?
Yes, definitely. Yeah. You want to speak on that? Or? No? Yeah. Yeah, you definitely can. I know they were talking about possible uses as if there was going to be new catch basins being put in, how much would be needed? What's the amount of water going through there to predict the size of catch basin that you would need to collect that? Yeah, it's definitely.
Do you have queue information for designated points such as catch basin, entering the storm drain network, or the queue at certain points of the storm drain networks?
I don't know.
Yeah,
Yes.
queue,
Yeah,
queue flow.
Yes.
No?
And some of the RQPs, there's a queue in there, but I'm not too familiar with what layers have that in there. Because that's a separate department handles the volume of flow. Yeah. There you go. Like, so yeah, but
I'm the guy.
so we haven't found a good hydro model to use to input the queue and then combine it with the trace network. So that's cool.
We're gonna be touched.
That's like phase 4, yeah.
Yeah.
Yes.
Are you looking, you're talking about it for years.
We have.
Depth of surface flow
Predict the depth of surface flow?
for a given storm.
We are so far is not that we are planning later on. So far we are doing that is a lot of trace network and then how we can trace. Then future we can, depending on how much of volume we can collect, that is a later step. We don't have information for that yet.
Okay, I'll just put, I mean, I'm not part of, we were part of a special district at LACSD, but we're interested in infiltration to local sewer animals. So, I'm sure that if we knew like depth above a manhole, it would probably be useful.
Yeah, we don't have that information right now, and then we planning later on get the information with the other water quality engineering. We'll get the information and see what we are going to do with this.
So if you're with Sand District, we know that you want this data, so we'll give it to you to calculate that. Yeah, that's good. Regarding the trace network, I mean, I understand that it doesn't look like you have any devices that require the utility network, but was there a decision-making process about going with the trace network, or was this mostly the trace network kind of related to the whole North Hydro? Is that why you chose the trace network over utility network?
We have before like a utility network, and then later on we have a trace network license, and then we do that. I think we have a.
It'll be implemented in a utility network once we have it prepared in a portal, and then build it out using Experience Builder. But right now it's just a simplified trace network.
Trace network is free.
That's free for now.
Utility network costs $20,000 to $30,000 a year. So we started with one, we'll transition to the other one.
To make it public facing, we're supposed to be able to trace it in UN, which then costs a lot more money. So we'll do that eventually. Setting up our infrastructure.
Yeah, we're getting started out in the UN. That's why I wanted to,
Okay.
okay, Bob.
Any more?
Anyone else?
Oh, God, I went too far. Thank you.
right on over here. Okay, hold on a second. Here we go. Okay, Ken, this for you. On over here. Yep. Then in front of you. There you go. And then, Julie.
All right, smile, one.
Right here.
Julie, 2, 3, 1, 2, 3. Then Debbie, keep still.
Thank you. Thank you. Thank you. Appreciate it. So we'll have a break right now for a little bit, and please be back here for our next talk at 12:45.